Hopefully the statistics chapter is really hammered home that whenever we're talking about a procedure, we need to have some idea of how good of quality the results are going to be. We want to know something about the accuracy and the precision of our information. Now, accuracy we can always fix by taking a standard and then adjusting our values to match up with that standard. That's just a matter of calibrating our system. But the precision is going to end up having a lot of different things built into it. Now, there's two different things that they're highlighting right here as the key pieces that result in error when it comes to our experiments. And this is actually out of the previous edition, the 7th edition of the Harris textbook. They've got a different marginal graph in the 8th edition, so I wanted you to be aware of that in case you were looking at the 8th ed and think it was the same thing. It's actually slightly different. Now, what we see on this axis is going to be our relative precision in percentage. So this is 1%, 2%, 3%, 4%, and 5% precision. This x-axis is going to be our absorbance. Now, just to highlight what we're talking about, though, I put in P0 to P ratio to highlight what we're talking about at each of those absorbances. When absorbance is 0, that means we have the 1-to-1 ratio. We divide one by the other, take the log of it. Log of 1 is 0, and so this ratio ends up being an absorbance of 0. Now, that's a spot that we don't care a whole lot about, obviously. We have to zero it out, but after that we're not so concerned. But this will give us some idea of what kind of precision we can expect at different measurements that we would do. Now, cell positioning error. Remember, what we're doing is we're taking that cuvette, and if we're moving it in and out of our sample holder inside of that instrument, what's going to end up happening is our light's going to be going through in a spot. Now let's really exaggerate what happens if we have positioning error. Oops. And we'll see how well I can draw as well. Here we are. Suppose that we end up having our cuvette on an angle. Notice how my path length has just changed. It's going to be dramatically longer. Dramatically to me at least. I mean, look at the length that we're talking about. It's going to be probably about 10% longer in the way that I've drawn it here. It would never be this terrible, but it would be something on the order of, you can see right here, something as high as maybe 4 point something percent error. So cell positioning is going to be a big issue. Now, how do they try to avoid that? Well, when you put a cuvette in, and I'm doing a top view of the cuvette, of course, there's going to be that box around it. And there's going to be a little metal spring right here. When I say a spring, I mean it's just a little curve of metal like this that's pressing up against it. So there's usually one on that side, and then maybe another right here, and another one right here. And that's going to help it stay reproducibly positioned each time. Now, of course, that means if your cuvette has any polishing differences, that's still going to end up showing up as part of your error. Now, instrument electrical noise, what does that exactly mean? Well, let's just picture what's going on. If we have a really high absorbance, then what we're saying is that no light should be passing through my cuvette, right? So basically, I've just turned off the light getting to my detector. So at that point, should I see any voltage fluctuations on my detector? Well, if the only thing causing that is the amount of light hitting it, no, we shouldn't see any change. It should just be a tiny number. But there's still going to be a little bit of flicker there. Now, some of that's just going to be just the normal static that your detector gets. Some of it's going to be random photons managing to get reflected off of surfaces in unexpected ways. Lots of other things like that. But when we're focusing on just the instrumental noise, it ends up having a big effect when you have nothing blocking it, and also when you have lots of things blocking it. So low concentration and high concentration. But overall, what you end up finding is that there's a sweet spot in the middle. So you end up having your absorbance kind of optimized right here in the 0.3 to maybe 1.2 range. And of course, that depends on the spectrometer. It depends on what you're going to call optimized. And so you'll see different numbers quoting different ideal ranges for your absorbance. But a lot of the time, what you're going to see is that people like to work in the 0.3 to 1 absorbance unit range. Now, I also want to emphasize this is for routine work, and this is on probably a fairly inexpensive spectrometer. If you work on a more expensive spectrometer and you take great experimental care, and it's something that you care about a lot, you can get good quality results even at lower absorbance ranges. But one of the things you'll find if you're using a decent quality spectrometer, it's pretty rare that they display more than this value in terms of absorbance. And that's just because in the fourth decimal place you start having a whole lot of jitter. Because think through what you're talking about at that point. You were talking about a 1,000 to 1 difference in the signals that it's looking at between P0 and P. That's a really big difference. And so for that kind of a range, we're going to be seeing a lot of noise, and you'll actually start to see a lot of jitter in these values. You're also going to start seeing a lot of other entangled variables that matter a lot when you take a course like instrumental analysis, and we really focus in hard on the instrumental error that's involved and also exactly what we can do with the hardware to try to improve it.